Hello everyone, I hope you people are doing well and staying safe during this pandemic. For now onwards, we will be starting with the next chapter, and that is going to be the states of matter. Now, we already know what is a matter. A matter is anything that is going to have mass and it is going to occupy space. Naturally, or mainly, we have the three states of matter, and those are the solids, the liquids, and the gases. Okay, apart from this, there is a plasma state, and there is another state, what we call it as BEC, B-E-C, Bose-Einstein's condensed state. Now here, we are just going to deal with the three states of matter, and those are going to be, the first one as the solids, or the solid state. Next one is going to be the liquid state of matter, and the final one is the gaseous states of matter. Now, in all these three different states of matter, it all goes with respect to how the molecules or the atoms or the constituent particles are arranged. When the constituent particles, whether it can be an atom, ion or molecule, when these particular things are quite tightly organized, tightly packed, as what we can see over here, if we consider all of these as the atoms. So if we see, all these particular atoms over here are tightly packed. In such kind of cases, there is no freedom of movement. Now, when there is no freedom of movement, this gives rise to the first state, and that is going to be the solid state of matter. So generally what happens here, all of these atoms or the molecules or the constituent particles are organized. They have come close to each other. They have been organized very tightly. There is no freedom of movement. That means these particular particles do not move freely. Of course, there is a vibrations among those particular atoms or constituent particles. When we observe the next state, and that is going to be the liquid state, again, it all goes with respect to the constituent particles, atoms or the molecules, right? So here, again, when we consider, if we consider these particular things as the atoms or molecules, okay, here, what is happening is, these particular things have a freedom of movement, but the freedom of movement is not that great. Okay, there is a still small amount of attractive power that has been present between the different atoms or molecules. Now, this state is called as your liquid state of matter. Finally, when we come to the gaseous states of matter, we see that there is a great space between the atoms or constituent particles, as a result of which these particles keep on moving around freely. Okay, now these are nothing more than your atoms, or you can also consider it as molecules. Or here, the molecules move freely. But here, the movement of molecules is between those of the gases and solids. So it's an intermediate state between the solids and the gases, right? Now, whether it is a solid, whether it is a liquid, or whether it is the gases, any one of these, that is whether it is solid, whether it is a liquid, or whether it is the gases. Now here, what happens is, all of these 3 points or these 3 states have one thing in common. And that one thing in common is nothing more than all of these are going to have certain amount of mass, and they are going to occupy certain amount of volume. Okay, extremely sorry. And they occupy certain amount of space. That is, nothing more than these things are going to have volume. Okay, now the point that we need to understand, the point that we need to discuss over here is what happens between these atoms, whether it is solid, liquid or gaseous. Let's take this into consideration. Now let's say over here that we have the atoms. Let's say this is one atom over here, or you can also consider it as a molecule. Doesn't matter. Now, between the two atoms or molecules, usually what happens is there is certain amount of force of attraction that is present between these atoms or molecules. These forces of attraction between the atoms or molecule, we call it as intermolecular forces. Okay, these are called as the intermolecular forces. Greater the intermolecular forces, greater it has an impact directly on the physical properties of that particular matter. Okay, now what I mean to say over here is that if this particular intermolecular forces of attraction between the atoms goes on increasing, what happens is it has a direct impact on the physical properties, such as the first one we can consider over here, the melting point, if we are considering that of a solid. Okay, so what is happening here is if this particular interaction between the different atoms in that particular solid goes on increasing, all these atoms are tightly packed. So more amount of energy is required in order to convert this particular solid into its liquid form. That is, more the interaction, the more the intermolecular forces, the greater is the melting point of the solid. This also occurs with respect to the liquid. Let's say these are the atoms or the molecules in the liquid state. Okay, now if the interaction, that is the intermolecular forces, increases here, now that has a direct impact upon the boiling point of liquid. So direct impact goes to the boiling point. Okay, now it does not just end up over here, rather it also has an impact on the viscosity of the liquid. So in short, if the intermolecular forces increases, first point is that it increases the melting point in a solid, and second point is that it also affects the boiling point in liquid as well as the viscosity in the liquid. Because of the attractive power between these particular atoms or molecule increases, now the particular liquid becomes more viscous as the intermolecular forces of attraction increases. Alright, so that is what it goes by. Now, it all depends upon, if we are considering the molecule, let's say there is a molecule. Now, it all depends upon the energy of this molecule. Okay, it all depends upon the energy of this molecule, whether to exist in a solid state, whether to exist in a liquid state, or whether to exist in a gaseous state of matter. When we consider a solid state, what happens there is the energy of the molecule is very less. Okay, so one point to understand over here, energy in the solid molecules is considerably very less, and the energy, on the other hand, in the gaseous molecules, these particular energies are considerably very high. Okay, these are the important points what we have to remember now. Why is this energy high in the molecule? Because there is a great space. These particular molecules can travel with a greater kinetic energy. While when we consider that of the solids, there is absolutely no freedom of the movement. That means these particular atoms, these particular molecules, constituent particles are organized, they are fixed in their positions. They are not moving. And hence their kinetic energy is less. Of course, there is a vibration movement over there, but when we consider that of the gases, these particular particles or the constituent molecules, these move with a greater speed and therefore they have a higher energy. So, the energy of molecule decides whether it's going to be in solid, liquid or the gaseous phases. Right? Now, let us consider the next section, and that is going to be the intermolecular forces. Now, intermolecular forces are nothing more than the weak forces that exist between the molecules. So, these weak interactions which are present between the molecules are called as intermolecular forces. These intermolecular forces are also called as van der Waals forces. Okay, now these van der Waals forces are classified mainly into three categories. Depending upon the situation, depending upon what is the force that is taking place, we classify the van der Waals forces into three categories. The first one, we call it as the dispersion or the London forces. Okay, it is given on the basis of a scientist, Fritz London. Okay. Second one is called as the dipole interactions, or we can call it as the dipole forces. And the third and the final one is called as the dipole induced dipole forces or interactions. So we have these three. First one is called as the dispersion forces or the London forces. Next one we call them as the dipole interaction or dipole forces. And the final one is the dipole induced dipole forces. Now, we will observe one by one of all of these three. When we start with the dispersion forces or the London forces. Now, let me tell you that this was introduced by Fritz London. Now, here, what happens is when we take a look into monoatomic molecules. Now, when I say monoatomic molecules, the molecules such as we have helium, argon, xenon, krypton, etc. Such kind of monoatomic molecules. Or when we observe about the homo diatomic molecules such as we can say as nitrogen, oxygen, correct. So such kind of, even you can say into consideration of the hydrogen gas, right? So whatever we have taken into consideration, one important thing that we can understand here is all of these particular molecules are going to be a non-polar in nature. That is, the electron cloud is symmetrically distributed, right? Now, if we consider that over here, so now here, let's say this is a monoatomic molecule, okay, and this is a central part, and that is a nucleus. Now, in this case, what is happening is the electron density is perfectly distributed in all the direction. So, therefore, here is a symmetrical distribution of electron density. Now, what happens here is, of course, we know that there are the electrons, and the electrons keeps on revolving around the nucleus. We know that, right? Now, here when these electrons starts moving, due to which this is going to cause a polarization in the molecule. Because of the movement of the electron, it causes polarization in the molecule. That means one part of the molecule, one part of the atom is going to have a larger negative charge. Wherever the electron moves, that part is going to be a bit electronegative or negatively charged. And therefore, let's say this, due to the movement of electron, what happens is the atom becomes something like this. This is your positive center, and here is where the electrons charge has been resided, and so this is a negative part of this. Okay, now this is going to influence the molecule which is beside to it, which is neighboring to it. Therefore, what it does is it is going to influence this other part in such a way that the other molecule generates positive charge over here and the electron goes to the other side. And this occurs momentarily. Okay, so this is all temporary, or we can call it as, this is just a momentary dipole moment. Okay, this is a momentary dipole which has been induced. Now, this causes an attraction. Okay, now this attraction, what has been built up between the momentary dipole and the one which has been induced. Okay, so therefore the momentary dipole in one particular molecule, that is over here, and there is the another one which has been caused, which this particular molecule has been caused to develop a dipole because of the first molecule. Okay, now this particular molecule we call them as the induced dipole, right? Now the attraction which is present between the momentary dipole and this induced dipole, we call this particular force, the force which is acting between the the force which is acting between that of the momentary dipole and the induced dipole. This particular force, we call it as the London forces. Now remember that the London forces are the forces which are in a non-polar molecules. Okay. Now, what are the important points that we have to remember here? Is that all these particular forces are going to be attractive in nature. Remember this point. These are attractive in nature. The second point that we have to remember is that the magnitude of the London force, that is nothing more than the interaction energy, is directly proportional to 1 by r raised to 6. Now r is nothing more than the distance between the two molecules, and this distance between the two molecules we call it as r. Okay, so r is nothing more than the distance between the two molecules. So these are the important points what we have to remember. Right? Now, one more point that we have to understand over here is that these forces act in a short range. Remember that this acts only in a short range. Okay, in a short range or in a short distance, and that is approximately of around 500 picometers. Okay, so these are the important points what we have to remember. When we observe the second type of the van der Waals force, and that is going to be the dipole forces. That is the dipole forces. Now, here, these are the forces which are going to operate in a polar molecule. Now, what is meaning of polar molecule here? When we observe a particular molecule having the atoms of different electronegativities, naturally what happens is the one particular atom which is more electronegative tries to drag away the electrons towards itself. Okay, so therefore what will happen is, if we do consider this as a molecule here. Now this particular molecule, let's say this is a side A and this is a side B. Let's say about this. Now let's consider that the A part of this particular molecule is more electronegative. So therefore what happens is that the electrons which were supposed to be shared between A and B, these particular electrons will start to move towards A, right? Due to which, what is going to happen over here is this A develops a partial negative charge. Okay, on the other hand, where is the part B, it develops a partial positive charge. Now, due to this, what will happen is this particular molecule has an influence on the neighboring molecule. Now, as a result of which, what will happen here, whatever the molecule is at the neighboring side, what will happen? This particular part will generate delta positive, this particular part will then generate the delta negative. As a result of which, there is going to be an attraction between the two neighboring molecules. Okay, now here, the interesting point that we have to understand is that the magnitude of the force, okay, how better is this particular force? This magnitude of force which is generated between the two molecules having permanent dipoles, this particular magnitude of force is, of course, is less than the force that exists between ions. That means between the two ions, for example Na plus and Cl minus, there the complete charge separation is there, like Na plus and Cl minus. So therefore, there what happens is the attractive force what is generated has a higher magnitude, while here we have the partial positive and negative charges. Okay, so therefore, of course, these partial charges, what partial charges we are speaking here is with respect to the delta negative or the delta positive ones. These have the charges which are less than the unit charge. Now, less than the unit charge, in a sense, it is going to be less than 1.6 into 10 raised to minus 19 coulombs. It is going to be less than this particular value. Okay, so therefore it has a direct influence on the magnitude. Now, there are certain points what we have to understand. Let us take over here a solid state wherein the molecules are polar molecules. Okay, let's say this is a solid state over here, and let's say these are the molecules. This is the one molecule over here, this is the second molecule over here. Okay, now let's take these particular molecules for our studies. Now, for a moment, let's say these particular molecules, what we have taken, these are polar. Polar in a sense, one side is going to be, of course, delta negative, one side is going to be the delta positive. Similar happens over here, delta positive, delta negative, right? Now, from the states of matter's introduction, we already know that these molecules are fixed in their positions, due to which these are not going to move. Okay, so therefore, whatever the molecules that we have, the force of attraction that is generated between the two molecules having a permanent dipole, these attraction forces, or we'll call it as the interaction energy. Okay, this interaction energy is directly proportional to 1 over r raised to 3 r cube. Okay, now this happens for the solid state because these molecules are in the fixed position, right? Now, on the other hand, we need to understand what happens in the liquids. So when we observe about the liquid, let's say that we have the next stage, and that is the liquid state over here. So when we observe the liquid state, let's say this is a section of the liquid state. Let's say this is one molecule over here. Let's say this is the another molecule over here. And let's say that these particular molecules are again, of course, let's say these are the polar molecules. Okay, so when we take these particular polar molecules, of course, we understand that one side is going to be delta positive, one side is going to be delta negative. Let's say that this is delta positive, this is delta negative, this is delta positive, this is delta negative. Now, when we observe the liquid state, these molecules have one more point instead of just a motion. They have one more extra point, and that one extra point is that these have a rotation motion. Now, when I am saying that rotation motion, that means whatever the molecule that we are taking into consideration, this molecule keeps on rotating. That means this dipole keeps on changing, right? So therefore, here in this particular case, the interaction energy, when we observe the interaction energy in this particular scenario is inversely proportional to 1 by r raised to 6. Now, again, of course, r is nothing more than the distance between the two molecules. So this is about our dipole forces. Coming forward with the third part, and that is going to be the dipole-induced dipole force. Now, in order to understand this particular dipole-induced dipole force, let us say that we'll take one example. Let's say that we have a container. Let's consider this as a container. Okay. So in this container, let us say that we have taken some amount of water. Okay. And in this, we are going to induce a pipe, and through the pipe we are going to pressurize in the helium gas. Okay, so and we are of course going to seal this up. Now, when you observe this particular scenario, when we observe this particular condition, what happens here is that we are pumping inside the helium. Let's say this is the helium gas. Okay, or this is a helium molecule. And surrounding this particular helium molecule, of course, what we have is a water molecule. And let's understand this case. Let's say this is a water molecule. Okay, now, water molecule, it's a polar molecule having a permanent dipole. Right? So, therefore, let's say this is a water molecule which is completely polar in nature, while helium molecule is a non-polar in nature. Now, due to which this water molecule as what we have here, what this water molecule will do? This water molecule, of course, is going to have a delta minus and delta plus partial dipole charges. Okay, partial charges over here. Now, this partial charges is going to influence the helium molecule. The way that it influences is that this will make this entire molecule to be polarized. That means it is going to distort this electron cloud of the helium molecule. Due to the distortion of helium molecule electron cloud, what will happen is one side is going to generate a partial negative charge and one side is going to generate a partial positive charge. Let's say this is how the helium molecule will look once the electron cloud is being destabilized. Okay, now due to which it occurs, due to which it forms now an attractive force with the neighboring molecule. The neighboring molecule, as what we had, was the water molecule over here. Right. Now, this of course has delta negative and this has a delta positive. Now, this interaction between the helium, this attractive force which is generated between the helium molecule and a molecule which has a permanent dipole moment, that is, this was actually a non-polar molecule, but it has been polarized now. Okay. Now, between a polarized molecule and a particular molecule having a permanent dipole movement, and this particular dipole movement is greater than 0. Okay. Now, this particular interaction, what we follow here, is called as dipole induced. That means this fellow is inducing dipole. Okay, so therefore this is called as dipole induced. That means this fellow is inducing the dipole in this dipole force. Again, the interaction energy when we observe, interaction energy is directly proportional, is inversely proportional to 1 over r raised to 6. Again, r over here is nothing more than the distance between the two molecules, right? Now, there are certain important things that we need to complete over here for the sake of the competitive exam. Now, the first point that we have to understand is that between the two molecules, the greater the size of a non-polar molecule, the greater is its polarizability. That means a greater is its tendency to get polarized. So, greater the size of non-polar molecule, greater is its polarizability. That means greater is the attractive power that has been formed. So greater polarizability, greater charge separation. Greater charge separation means greater force, that is the dipole induced dipole force. So therefore, taking that into consideration, we can say that a xenon, okay, is going to form more dipole-induced dipole forces when we compare to that of the helium in water solution. Okay, so therefore, xenon water solution is going to be more consisting of the dipole-induced dipole forces when we consider that of its relation with helium water solutions. Okay, so this is going to be more polarized because of the greater size of the xenon. Okay, therefore, greater the size, greater is the polarizability. Greater the polarizability goes with the greater dipole-induced dipole forces. This is how it goes. Okay, I hope you have understood the three different types of van der Waals forces. Take care. Have a great day.